Welcome back, everybody. Got a full house today. Yes, don't look so thrilled. She's like, it's okay. We're thrilled. So schedule stuff. We have a quiz to go over today, formative assessment, excuse me. Homework due next week. And next week, I just wanted to point out, you only have one day of class. I will be out of town. So
going somewhere fun.
Does Baltimore count?
Yeah.
It's a conference. So we're heading out. The aquarium in Baltimore? Okay.
Good to know. I have to go there.
I've only been there one time, and it was for another conference, so I didn't venture very far, but that's good to know. So yeah. So let's go over our quiz first thing here. So as a reminder, you get points for doing it. I'm not grading these, just looking to see that you made an honest effort. So questions. First one here. In null hypothesis significance testing, what is the role of the null hypothesis? So general question here. What's the role of a null hypothesis?
Gives us something we can test against.
Yeah, a benchmark. It can be no association. That's pretty common. If you're comparing, for instance, a mean or a proportion to some known value or some expected value, that's your null. Good. What does it mean if you say that you reject the null?
Found something significant.
Found something significant. Something unexpected. So if the null were true, what we found would not happen very frequently. Yes. What does it mean when you say that you retain or do not reject the null?
There's something that's non-significant?
Non-significant. Not insignificant, right, but non-significant. Something within the realm of expected variation. So we don't have enough evidence to say that the null is not true. Good. Type 1 error and Greek letter used to represent it. What's that? Alpha. Yes. Alpha is used for lots of things, by the way, not just this. Just, because there's only so many letters you can pick from, apparently. What is a type 1 error?
It's a false alarm.
False alarm, yes. So it's saying that you reject the null when in fact you should not have. It's a fluke. And we set the fluke rate by setting our alpha rate, right? So we decide a priori that we're willing to accept, say, a 5% fluke rate. 1 in 20 times we'd find something as extreme if the null were true. If you want to be more certain, do you make your alpha go up or down?
Yeah.
Down, yeah, fluke rate down. So like for instance, an alpha of 0.01 means only one time out of 100 you would find something and have it not really actually be there. Type 2 error in Greek letter. Beta, yes. And what is a type 2 error?
False negative.
Yes, false negative or a miss. So you should have found something, but you didn't. Probably because you didn't have enough sample size. And yes, I'm warm. We're getting the mommy hair again. Body temperature is such a subjective thing, but it's so different standing up here like trying to use your brain. I swear like the heat is coming out of my cells here. Like trying to make sure I say everything properly is, it generates a lot of heat. That's all I can say. There we go. That's better. All right, so we got those. What is statistical power, and what are the two factors that contribute to it?
Finding something when it's there.
Yes, the probability that you found something when it's really there. How does it relate to type 2 error? Yes, it's the complement. Is that the right word? Math people? It's not the inverse, but it's like the opposite. I'm looking for the math word. Is it complement? Okay, well, it's the 1 minus beta. We'll take that. So if type 2 error rate is 60%, what's your power? 40%. Yeah. What is conventional levels of power that we desire to have? 0.8. Yeah, 80%. Which means that our conventional level of type 2 error rate is what? 20%. Yeah. What are the two factors that contribute to high power?
Sample size.
Do you want more people or fewer people?
More.
More. How about the other one?
Effectiveness.
Effect size. Do you want?
Right.
Yeah, effect size.
That sounds good. I'll say it loud.
Yes. So, do you want more or less? More. Yeah, effect size is the strength of the effect that you're looking for, regardless of significance. Whether or not it's significant depends on how many people you have. So, we have effect size, which you can then create a test statistic from, like a t, and always in calculating a t, degrees of freedom show up. That's where sample size comes in. So for more power, you need a bigger effect, and you need more people. How do you know which type of bivariate association and corresponding effect size you should use? Give some examples.
Based on the type of variables that you have.
Yeah, such as?
Categorical and categorical.
What would you do in that case?
Chi-squared, right?
Yeah, Pearson's chi-square. And then that's the test statistic. You can then convert that into an effect size such as an odds ratio, a risk ratio, an R, which is not always the same thing as a linear relationship. So I added something to one of your slides from last time because I wanted to make sure that this was not confusing. I think it's one of the very last slides in Lecture 3 on this topic. Yeah. This right here. This is slide 44 in Lecture 3. So we can compute we can compute, meaning the software will do it for you, a Pearson's chi-square between two categorical variables. If both variables are binary, that is the same thing as a Pearson correlation. It's called a phi correlation in that case, but it's the same thing. It makes sense to be able to talk about a linear relationship between two binary variables because there's only one unit between them. So a line between the two is the only thing you can possibly have. There's an adaptation on this slide for when you have numerator greater than 1, which happens when you have one of your variables have more than two categories. In that case, this R that you're computing, this effect size, is not the same thing as a linear relationship. Because it doesn't make sense to think about a linear relationship if you have more than a binary variable. Like if you have something like dog, cat, bird as your favorite pets, you can't put a line through that. That doesn't make any sense. But what you can do is compute this effect size that describes the overall relationship. And that takes into account the fact that you had to basically estimate two different parameters for three categories. We'll get to that in terms of modeling to be able to do it. So this R right here is not describing a linear relationship between your categorical variables. But it is an effect size to describe their level of association. R gets used for lots of things, but I wanted to make sure that I pointed that out. Okay. So if you don't have categorical variables, what else can you do? What's another one?
If you have binary commutative variable,
Yeah, what would you do in that case?
like a point by serial.
And that's the same thing as?
I have
Point by serial is what she said?
Oh,
Yeah, it's a Pearson's.
I said that.
Yep, it's if one of the variables is binary, you can shortcut the formula, and that the name of that shortcutted formula is point by serial, but it's the same thing.
Okay.
Yep. Yep. And one more that we talked about that's on the slide.
Binary variables.
Uh,
Spearmint.
yeah, a Spearman. Spearman's for ordinal. That one doesn't lend itself into modeling, so that one's gone after today. Bye-bye, Spearman. So, thanks for playing. Yes. All right. So, in terms of power, this is the reason, these two factors, the idea that you'll have more power, more chance of finding something that's there, the more people you have is why we can't ever say that we accept the null. Given enough people, the smallest deviation from the null will be significant. So all we can say is that we do not reject. We don't have enough evidence right now to say that, but we could if we got more people for the same level of effect size. All right, so questions on any of this? All right.
I don't really get that because if you're running your test with your samples and your variables,
Mm-hmm.
and for for your intents and purposes, you would like to accept the
Mhm.
null. Why can't you say that for your study and your investigation?
So someone's going to yell at you. I mean, I agree with your rationale. Like if you're limiting your your conclusion, but in theory, what we're doing with the sample is trying to make an inference to a population. So it says even though you only took one stab at it, you're trying to like predict what would happen for anyone taking any stab. And so the answer that you make is supposed to generalize to that case. So, but yeah, I agree with you. But yeah, just don't say that. Yeah.
So in this example, so I'm doing a study right now, and I would like my survey to have similar, the sample be similar to the sample of the teaching force, right? So if the teaching force is, let's say 85% white and 82% female, let's say, wouldn't it be good?
Good.
Like
You can say
if
good.
my sample, so if I found that my null hypothesis would be against that, let's say 85%, and if I find that my sample is also 85% females, then I wouldn't be rejecting the hypothesis. I'd be retaining it.
Okay. So
Maybe all those things.
no. So I think I follow you, but let me make sure. So you are trying to make sure that your sample is representative of a population in which you know it's supposed to be 85% white, 82% female, et cetera, et cetera. And so in order for you to have some evidence that you are representative, you want to make sure that your numbers are not different than those. So that's still the null, but in that case, a decision of significant is bad.
Yes.
Not good, as you said. So it's not good. Yeah. So if you retain the null, that's what you're going for.
So
in
that
your
is the thing,
specific. Yes,
to
it is.
To go for it.
Yes.
I just don't have
Going for the null.
I don't have, I'm going for the null, people. I just don't have the vocabulary to like.
No. That is a thing, and you're not the only one to do that. So in advanced statistics, when we start talking about model fit, for instance, it's how well does your model capture whatever pattern of correlation there is amongst a set of variables, and whether that correlation is high or low is immaterial. It's how well your model captures it.
Yeah, that's
and in
right,
that
yeah.
case, like you want it to be not different.
Yes.
Like you want to keep the null, retain the null. And that's an okay hypothesis. You just have to be careful because if you didn't have enough people, you're going to keep the null.
That's what you were just. Okay.
Right. So like if you want to get 5 teachers, right, and then you're hoping 4 of them are white, right? If you're like you don't have any power to say that is representative.
Yes, you're right.
And so then you could stack the deck in that way and keep the null because you've set it up so that there's no chance of you rejecting it.
So in that sense, can I go to the tables and get 46 respondents in order to get 80% power to make that good that I retain the null?
You don't want power in this case.
That's where I try to throw all of it together. Okay.
Yeah, so I mean, you
okay.
want enough power so that you can say to any detractors that you didn't stack the deck in your favor.
Okay.
You want to have had a decent shot at rejecting the null. But you personally do not want to do that because that conclusion would be that you screwed up your sampling.
Okay.
Okay, with me?
Yeah, I am. Yeah.
All right. So accepting, rejecting, right? It's a qualitative judgment as to which you want to happen. It's just that the null hypothesis is the benchmark that you're judging against. That's the thing to kick out of this. So, question or just waving? Stretching? Okay. All right. Other questions?
It's a weird problem, but then is ever an issue having too many
Mm-hmm.
worker sample? Well,
Absolutely.
not as many mistakes.
No, it is. So, like the EPLS folks, do you have big samples? Like if you're looking at archival data of like all the students in a state or something? This also happens in like political science where people are studying like huge cross sections of people from countries. Yeah, so if you're trying to make a judgment as to what are the important factors in predicting some outcome, and everything is statistically significant because you have so many people, then that is a problem in the sense that like that's not a good marker for you to focus on. Then you'd really want to go with some sort of effect size cutoff. Like it has to be an effect size bigger than this for me to practically care because everything is significant. Yeah. Mm-hmm. Good question. Other questions? All right, any homework questions? You're working on homework 2? Not yet? So I did have one question today that I wanted to go over real quick in case someone else has the same question. Let me find it. So testing a sample proportion. Just to remind you, the default behavior of SAS and Stata is different in this regard. So this is the data set where we had a variable that was called female. And the variable is coded 0 is male, 1 is female. That's what it means. In SAS, the default behavior is to test the proportion of zeros, which would be males in this case. In Stata, so it's focusing on this 61%, and you can see that by repeating the proportion it's testing, and it gives you a confidence interval around it. So it's focusing on the proportion of zeros as its unit of interest. The default behavior for Stata is exactly the opposite. It focuses on the 0.39, the 1, and gives you a confidence interval and a significance test around that. So I gave you 2 questions in your homework, one asking about a 0, one asking about a 1. So no matter which program you're using, you'd have to learn how to recode to get the other one. And so in SAS, it would look like this. So I'm starting with the variable that is in the data set called female. I am generating a new variable called male because I intend for it to be 1 if it's male. Dot means make it start at nothing, missing values. If the old variable is 0, then the new variable is 1. If the old variable is 1, the new variable is 0. And then I put male into the proc freq instead. The same idea in Stata looks like this. Gen male means make a new variable. The dot means make it missing. And then replace, and the order of the variables is different. So after replace, it's the new variable first. If the old variable and then equal, like it's a conditional logic thing, whenever you have that, that's what double equals means. So male is the new variable, female is the old variable, and then I test male to get the other one. All right. Okay. Are there any other homework questions that I can help with so far? Nope. And in this one, if you haven't logged in, you'll see that there's no results section to fill in this time because there's not a whole lot of things that are new there. Instead, I asked you a whole bunch of multiple choice questions about what your results mean. So those questions pertain to your results and what you found. So each of you will have a different answer depending on the exact content of your data. All right. Then if no one else wants to talk about that stuff, then we'll go on to something new. General linear models. I'm so excited about this. So we're in lecture 4 for the week here. We'll see how long this takes. Lots of new vocabulary, lots of new language, no new concepts. You got it? You ready for this? Ready as you're going to be, right? Okay. So we did this last time, but it won't hurt to review again. So review the univariate and bivariate stuff we've learned so far. So examples of testing hypotheses, again, about univariate distributions, such as the means. So one sample z-test is when you're testing some kind of mean against where the variance is known. That's what happens in a proportion test. One sample t-test is what it's called when you're testing a sample mean and you don't know the variance. That's, for example, whether or not your case, actually, damn it.
Kelly.
Thank you. I was going to say, I know it was K, I was getting there. Kelly wants to know if her sample has the right proportion of white versus non-white people. That's an example of the latter here, where you're going to have to estimate the variability of around those numbers. Bivariate, we learned. Pearson's linear relationship between two variables. We do a t-test to compare that R against a distribution where the null hypothesis is usually 0. Spearman's rho doing the same thing on rank order data instead, and chi-square for categorical. So those are the things we know how to do so far. Moving on. And this is the part where the way that I want to teach this is going to be very different than what has been done in the past, so you guys are an experiment. But I mean that in a good way. Because if things don't make sense, or if I use words that I haven't defined yet, it's not your guys' fault. It's my fault. So please do not feel ashamed or embarrassed to ask questions, because I've never tried this before. We're going to see how it goes. But I always said in my advanced classes, if I ran the world, this is the way the introductory classes would have been taught, so now I'm putting my money where my mouth is. We're going to do general linear models from the get-go. So predictive linear models. The idea is that now, rather than just talking about two variables or one variable, we're designating them as predictors versus outcomes. Do you remember the difference? An outcome is something to be explained. A predictor is an explainer, a reason. So which is which depends entirely on what you want to know and how you're phrasing your own question. But everything from this point on, we're going to have each variable play a designated role as either a predictor or an outcome. So the models that we use to predict outcomes have different names depending on what kind of outcome you're predicting, what type of variable it is. So if you're dealing with an outcome variable that is quantitative, that is continuous, or what I called continue-ish, things that are quantitative that might have a boundary or so, what we're going to do, general linear models. The term general refers to quantitative outcomes. So we're predicting quantitative outcomes, and we're using the normal distribution to do so. That's us. Every other kind of outcome falls under a different word. Generalized. That means some kind of not normal outcome. That's the class I'm teaching in the spring. So I'd encourage you to come back if you have the chance to do so. But just to give you a sense of what these would look like, what these models do is predict either categorical outcomes or quantitative outcomes that have boundaries. And they do so by choosing a different distribution for what the variables should look like and transforming the predicted outcome to deal with the fact that there's these boundaries. So for instance, binary outcomes, whether it's just 0 or 1 and that's what you're predicting, the distribution that goes with that is called Bernoulli. We saw that before. It has one parameter p, because once you know how many people have a 1, you know how many people have to have a 0. So there's only one parameter. The variance is determined by the mean. But if we want to predict whether or not somebody has a 0 or 1, the model has to understand that the highest possible value that can be predicted is 1, and the lowest possible value is 0. And so this thing, this idea here, this link function, that is a transformation of the predicted response that makes that happen. So you've seen an example of this sort of transformation so far. Do you remember the Fisher R to Z transformation? Remember that? Maybe? Let me pull up a picture of it. It was in this one. I have a picture. There it is. This is an example of a nonlinear transformation. It's designed to extend the boundaries of the correlation past the highest and lowest it can go of -1 and +1 so that you can compute a confidence interval. And so this is an example of the type of transformation that one would use for a bounded outcome, where it doesn't ever stop. As the closer and closer it gets to 1, it keeps going and going and going and going. So those sorts of transformations get used in predicting outcomes that have boundaries or categories. Count outcomes is another example of that. Counts can't go negative, so the log transformation is used to keep the predicted counts positive. Something else is used for binomials to keep them within the boundary of 0 and 1. So, question?
Okay, so this might be going really far back, but when you're talking about a model.
Mhm.
So, like, how is a model different than anything that we've been doing?
We have been doing bivariate associations without designating which is the predictor and which is the outcome, because it doesn't matter when you only have two. It starts to matter when you have more than two variables involved. And if you want to know the association between two things, factoring in another thing.
Can I have
Then-
an example of that? Can I have an example of that?
Sure. To what extent is screen time bad for your preschooler after you control for the amount of time you spend reading to them?
So this is like so creating a model is like the after you control for.
Mhm.
So it's manipulating more stuff.
It is doing via statistics what you wish you could have done by design.
Oh, that makes sense. Oh.
So if I said, what is the correlation between screen time and preschool outcome? That's one number. What's the correlation between parent reading and preschool outcome? What is the correlation between parent reading and screen time? A model takes into account all three of those things to be able to answer the question, is screen time still bad for you after you control for reading or lack thereof?
Thanks.
So we're starting with just bivariate associations. But what we're going to do is see what it looks like in the context of a model and then add more predictors to it so that we can talk about the idea of unique effects after controlling for. So all of these things, I just want to point out, you are not forced to only have models for normally distributed outcomes. There are other kinds of models for other kinds of outcomes. We just can't get there in one semester. But come back. Okay. So what are we going to do? General, that word means quantitative variables. We're using a normal distribution. The next word, linear. The term linear means a model that has this form: constant times variable plus constant times variable plus constant times variable. So there's no logs, there's no e to the, there's no exponents, there's none of that. So this is what it means to have a linear form. All of our models are going to look like this. This one here is technically a constant as well, but that is necessary in order to make the scale of what is predicted equivalent to the scale of this. So our models are all going to look like this, where we have y sub I. Remember what that is? What does that notation mean?
Person I.
It is the y outcome for person I. So yeah, that means y for each individual. That's what I means. Is a function of some constant times 1. So that's in there just to keep the form the same. Constant times an x predictor sub I. So that would be the x for person I that goes with this predictor. Plus x, looks like my I got dropped off of that one. Let me fix it. X predictor 2, and so on. So the fact that we have this type of linear equation does not preclude us from looking at nonlinear relationships. As an example, what type of relationship would it look like if I took this x predictor 1 and squared it? What kind of line would I be predicting? Yeah, a parabola or a U. Yeah, exactly. This, this. So it's still a linear model to get a U-shaped prediction. So linear doesn't mean that we don't have only, that doesn't mean that we're forced to keep only linear relationships. It also means that this X predictor doesn't have to be a quantitative variable. It can be a binary variable. So we can have whether or not you're white or non-white, for instance, as X predictor. So the general linear model, again, the idea just that we're predicting a quantitative outcome using a normal distribution. We can have any kind of predictors we want. We can have main effects where they're additive, or we can also have interaction effects where the effect of one predictor depends on the other. Historically, these different classes of models get different names depending on what kind of predictor variables are included. And they are often taught in completely different classes as well. which to me is a huge disservice because it makes it seem like they're different and they're not. So there's a class called, in this university in my department, called Correlation and Regression. That just means you have continuous predictors, quantitative predictors. Analysis of variance is what this is called if your predictors are all categorical. This word, by the way, is ANOVA. It's always ANOVA. I've heard many different pronunciations. ANOVA, ANOVA, it's ANOVA. This one, ANCOVA. Analysis of covariance is what it's called if you have quantitative predictors and categorical predictors. To me, these words don't mean anything. They're just distractions. But I present them because if someone says, oh, did you take an ANOVA class? I want you to nod your head and say yes, because this is an ANOVA class. Did you take correlation and regression? You're going to nod your head and say, yes, you did, because this is a correlation and regression class too. We just did correlation. Now we're going to do regression. So this is the GLM, the general linear model. So, new notation. Our general linear models have different names depending on how many outcomes we're predicting at the same time. For the next several weeks, possibly the rest of the semester, depending on how long it takes, we're going to be in the world of univariate general linear models. Remember what univariate means?
One variable.
One variable. So one outcome. We're predicting one outcome. So one y sub I being predicted at a time. It is possible to predict more than one outcome at a time, but that requires a multivariate model. The starting point for any model is to represent the outcome variable that you're trying to predict. So central tendency and dispersion, that's what we do first. That's what the model is going to give us back. Because we're going to use the normal distribution within these general linear models, the model is going to give us parameters to describe the mean of the outcome and the variance of the outcome. That's the starting point. From there, we enter predictors to try and customize that mean and hopefully explain away some of the variance. Skewness is going to be 0. So normal. Do you remember what normal means? What that picture looks like? Yeah, symmetric and continuous. Can you think of any outcome variables that are perfectly symmetric and continuous? They're hard to come by. But that's okay. Because when we say that we're using the normal distribution, what we're actually talking about is that the residuals of the distribution are going to be normal. What the hell does that mean? The part of the outcome that is left over after you factor in your explainers, that's supposed to be normal. So it's not a big deal if you start off with a quantitative variable that is decidedly non-normal. That's not necessarily a problem. The analogy that I use for this is if you go to a store and you're trying to put on like formal wear, right? Do you remember like shopping for your prom dress or like a tux for your wedding or something like that? Yeah, that face, exactly. And if you do that and you come to, to Kohl's or wherever you get your formal wear, that's where all my clothes come from, Kohl's pretty much. And you're standing there looking at yourself in the gown and you're like, what would this look like if I had heels and a decent bra on and my hair wasn't in pigtails? Like, can I just visualize like that, right? And then the guys, it's like, what would it look like if I didn't have like my ratty tennis shoes and a crappy t-shirt and like you visualize like what it could be. It's like that. So it's not that your outcome has to be normal. It's that like the end result after all of your fussing and finessing has to be normal. That's the assumption that we're going to make. The end result. So that being said, we start with no result. Your very, very first general linear model. It's called the empty model because there's no predictors. So more new vocabulary. Y sub I, y for each person, equals beta sub 0. So usually this is just beta 0 to me. Sometimes you'll hear people say beta not. No, just no for that. Good. It's not beta sub 0 for reasons that I can't explain. It's y sub I but beta 0. More generally, betas are what's known as fixed effects. They are constants in our linear model equation. So this beta 0, it doesn't have an I. Everybody is going to use the same number to develop their own predicted outcome. The 0 is a counting index. So we start counting at 0. The next beta will be 1. The beta after that will be 2. So it's just keeping track of which is which. So in the empty model, if you don't know anything else about a person, what is your best guess for what their outcome is going to be for any variable? The mean, yeah, the most likely outcome, right? You don't have any other way to do it, so let's guess the one that's the most likely. So if I said that we're going to predict this blue variable right here, what is your best guess for that blue variable's beta 0? 0. What's your best guess for the red variable's beta 0? 0. Huh. Now those don't look the same, but beta 0 would be the same. What's the difference between the red line and the blue line? Variance, right? How far off each case is from the mean squared. Square root of that being standard deviation. So if beta 0 is my best guess, this is called the intercept. This is what all models start from. Sometimes it's called the constant, but UG, because all fixed effects are constants, so I'm not going to use that term, but that's what Stata calls it, by the way, the constant of the equation. This beta 0, the intercept, has a very special definition. It is the expected outcome when your model predictors are 0. Right now, I don't have any model predictors, so it's my expected outcome. The most expected outcome is the mean. What if I was predicting the green variable? What's beta 0? Yeah, -2. Very good. You got it.
Could you repeat the definition?
Yeah. Yep, I'm reading it right here, actually. It's the predicted or expected y sub I outcome when all the predictors are 0. So expected or predicted mean the same thing. Because we don't have any predictors yet, it's just the expected outcome, which is the mean. But we also got to know the variance, you said, right? To be able to differentiate which of these variables we're predicting. That's our friend E here. E sub I, E for each individual, this is what's known as a residual. It's the difference between the actual y sub I outcome and the one predicted by the model, the fixed effects of the model. And I have an extra space in here for no reason. Here we go. So in this case, E is the difference between what you actually got for y and the mean. This should look familiar. This is the definition of variance. Do you remember variance? It's right here. How far off each y is from the mean, squared, so that we don't accidentally cancel out the positives and negatives. Sum that up over people and divide by n-1, because we've lost 1 degree of freedom by estimating the mean. Same exact thing, new letter. E is how far off your predicted y is from your real one. Right now, predicted y is just the mean for everybody. So I can write this the same instead of saying y sub I minus the mean, it's just e, because that's what e means. So before we called this the sample variance, and we denoted it as s squared. New symbol, same definition, sigma squared sub e, the variance of the e residuals. And yes, we've switched to population notation. Because we only have one sample, we're trying to make inferences about a population. So we just sort of assume that everybody recognizes that, and all of the notation is population notation, which is why we use betas, which is why we use sigma squared rather than s squared. So I told you no new concepts, right? Just new vocabulary and no symbols. So all this is doing is spitting back the variable's mean and its variance of the e's. So this model has two parameters. Parameters is a word that means thing to be found, thing to be estimated, a fixed intercept, and an e variance across people.
Things to be.
Found or estimated. Things you don't know that you are trying to find using your data set. Parameter. Fixed intercept, that's the mean in this case, and then variance of the e's across individuals. Questions? Okay, so this is our jumping off point for every model. This is the beginning of modeling. If you don't know anything else, best guess for each person, the mean, because that's the most likely value. And we have an estimate for how much variability there is to be explained. So why is it that some people are higher than the mean and other people are lower than the mean? I don't know. That's what E means. It stands for error in the sense of unpredictedness. Is that a word? In prediction? Unprediction? A prediction? Stuff you don't know yet. How's that? E is stuff you don't know yet. Why are some people above the mean and other people are below the mean? I don't know. We're going to find out. So, beyond that, our job is to add predictors. So we're going to start with just one quantitative variable at a time, and that is called simple linear regression. Linear, in the same way that it's a general linear model, constant times variable plus constant times variable. Simple in that, not like, duh, this is like so simple, but like simple as opposed to more complicated by having more than one predictor. So let's say that I want to use a model to give me a Pearson's correlation between two variables. Because that's the first step in trying to figure out whether that correlation stands after controlling for other things. So let's say that we have two variables. They both have a mean of 0 and a standard deviation of 1, so that makes the math easy. And they have a Pearson's correlation of 0.5. So let's not worry about significance for right now, but just what does this number mean? These variables are associated how? Positively, meaning that as x goes up, y goes up, right? So if you're higher than the mean on x, you tend to be higher than the mean on y. So let's say that this is screen time and amount of joy that your child brings you. How's that? Children who have more screen time give their parents more joy. That's my hypothesis for today. So another way of writing the same idea of a Pearson's correlation is by designating one of the two variables as the outcome, in this case parental joy, and X as the predictor, screen time. So joy for each individual is still a function of the fixed intercept. We keep that, but now we're adding something. We're adding another beta. It's the next one, so it's beta 1, and it's the association between X and Y. X being screen time for today, Y being parental joy. Beta 1 is a slope. Now, all of you told me this, right? I gotta do it this way, right? You know what a slope is, you just did it. But you probably learned about this in like algebra, long time ago, maybe. It's the change in Y per unit change in X, rise over run. If that makes you squishy and I can see it on your faces, just do this. So if these things were completely unrelated, what would my slope look like? If they were negatively related, what would my slope look like? Yeah, this is positive. There, I kind of look like I'm, like, you know, walking like an Egyptian or something here. No?
The Bengals, I love
They, yeah, I love the Bengals. But yeah, it's called Walk Like an Egyptian. Ask the YouTube after class. But yes. So yeah, you have an intuitive sense of this, right? It's the change in Y, difference in Y, for a 1 unit difference in X. The formula for the slope, you can get that out of the Pearson's correlation, the standard deviation of the Y outcome, and the standard deviation of your X predictor. In this case, I made the values so that the math would be nice and easy. The slope is 0.5 because X and Y share the same scale. Beta 0 then, expected outcome when X is 0. That's my fixed intercept. The formula for that is the mean of Y minus the slope times the mean of X. Works out to be 0. So putting it together, if I have a Pearson correlation between two variables, each with a mean of 0 and a standard deviation of 1, my general linear model to describe that correlation would have a beta 0 fixed intercept of 0. So that's the expected Y when X is 0. From there, the slope of X is 0.5. So for every unit higher X, Y is predicted to go up by 0.5. For every unit higher X, Y is predicted to go up by 0.5. So note what is not on beta 0 and beta 1. They don't have eyes. They're fixed effects. They hold for everybody. So anybody with an X of 0 has a predicted Y of 0 as the intercept. Anybody with an X of 2, for instance, would have a predicted Y of, if X is 2, what is Y according to this? 1, yes. Thank you still, Jeff. Yeah. So each of these linear models is going to have one intercept because the job of the intercept is to adjust for the difference in scale between the mean of Y and the mean of X. It's going to have one or more beta slopes pertaining to variables. So for today, we have one X at a time. But can you guess what would happen if I added another one? What would its beta be called? 2. And another one? 3. And another one?
4.
There you got it. Yes. Now E here, error, unexplained, same definition, different value. E is always the difference between the actual Y and the one that is predicted by the model fixed effects. Now, E is going to be different because everybody's predicted Y is not just the mean. It's an adjusted mean. It's a custom mean based on what your score is on X. So you told me a minute ago that if I have an X of 2, my predicted Y is 1, right? Anybody with an X of 2 gets the same predicted Y. But those people aren't going to have the same real Ys. So how far off your predicted Y still is from your real one? That is E. So to be able to convey this, what predicted Y is, we have another new symbol. Y hat. That is meant to capture the red part of the model here, the fixed effects. So you told me predicted Y for somebody with an X of 2 is 1. So Y hat would be 1 for that kind of person. What is predicted Y for an X of 0? Zero. What is predicted Y for an X of minus 1? Minus 0.5. How about minus 2 for X? Minus 1. Yeah. So this just captures the prediction in total from the intercept plus the effect of any predictors. So writing that, plugging in my hat here, real Y equals predicted Y plus some degree of offness. Residual, yes, E. So what if my real Y is higher? What if I was predicted to have a Y of 2, but my real one is 3? What's E going to be? 1. So if my real Y is 3, my Y that's predicted from the model fixed effects is 2, E is going to be a positive 1. If my real Y is 1, and my predicted Y is 2, E is negative 1. Yeah, so E is supposed to have a mean of 0. E's are offnesses, deviations, residuals. All those words mean the same thing. So it's how far still you are off. So same formula for variance here, but rather than just guessing the mean for each person as what they're expected to have, we use Y hat. Y hat is a custom mean prediction. It's adjusted based on their value of X. So E should be smaller than what it was before. So this idea of variance of the E's that remains after factoring in the predictions from your X variables, that's called residual variance specifically. When you hear the term residual, think leftover. Leftover variability that we still don't know why it is. Why are some preschoolers more likely to bring their parents joy? Well, it's not because of screen time. We factor that in. Do you remember testing a Pearson's correlation using a t-distribution? That factors in sample size, how trustworthy that R is given how many people you have. Same thing. The model at this point has 2 fixed effects, beta 0, beta 1. That means we lose 2 degrees of freedom. So we'll use the t-distribution to test this model against the null, that there's no relationship, that there's no slope. Okay. So, no new concepts. Linear relationship between 2 variables is captured by Pearson's correlation, right? This is what it looks like in a model, where the variables can have whatever distribution they want. So the slope and the intercept adjust based on the scale. So this is what it looks like if both variables have a mean of 0 and a standard deviation of 1, and there's a Pearson's correlation between them of 0.5. That's what we just did. What if X has what's called a t-score distribution, mean 50, standard deviation 10? Beta 0, the intercept, and beta 1, the x-slope, have to adjust. Beta 1 becomes 0.05. So now, a 1 unit change in x relates to a 0.05 change in y. Because x has a lot more units now. Each one has a lot smaller contribution. Because the mean of y is higher than the mean, the mean of x is higher than the mean of y, the intercept has to adjust too. So the intercept would be 2.5. That would be the expected y for my x of 0. For every unit higher x, y grows by 0.05. What would the slope be, do you think, if I told you the Pearson's correlation were negative 0.5 instead? Not a trick. Same number, backwards, minus 0.05. Slopes can be positive and slopes can be negative, just like Pearson's correlation can. What if we change the scale of y and keep x the same? If y has a mean of 50 and a standard deviation of 10, then the fixed intercept would be 50. So that's the expected y when x is 0. For every unit higher x, y grows by 5. So this is to say all three of these are equal in terms of the amount of association. The intercepts and slopes are scale specific. A word for that is called unstandardized, meaning they're in the metric of the original variables. The standardized slope is the Pearson correlation that you already know. That's the slope if both variables have a mean of 0 and a standard deviation of 1. So let's use some real data. I'll show you how to do this in SAS and Stata next time. But we're digging into the same data set that we've been playing with, the General Social Survey. Y is going to be family income in thousands. X is going to be education. So a general linear model that would examine the extent to which family income is predicted by education would look like this. Beta 0, when I estimate this model in SAS or SPSS or what have you, is estimated as negative 52, and beta 1, the fixed slope for education, is estimated as 6.6. I can take those raw numbers in the original metric of the variables, and I can standardize them by computing a standardized version of the slope, meaning a Pearson correlation between them with this formula, and it works out to be 0.45. So you know what a correlation of 0.45 means. You don't necessarily know what a slope of 6.6 means. Bang. So here's a picture. If I were to z-score family income and education and estimate a general linear model using education to predict income, that slope is on the left-hand side. That is my standardized solution, where the intercept is right here. It's the expected family income y when education x is 0, which is right here. And then the slope here for every additional standardized unit of education, standardized income goes up by 0.45. Same idea, same association, using original variables instead, because that's what we tend to do in modeling. The lowest value of years of education in this data set is 5, and the highest is 20. So I had to extend the regression line out to here to show you what the intercept is. So if you never go to school, your average income for your family is predicted to be in the hole by $52,000. It's not good, right? Does that make any sense? No. Now mathematically, that's fine, because a line, you can make a prediction from it wherever it is, but in terms of like us answering research questions with these numbers, it's just plain weird. The slope makes sense regardless of where the intercept is in this case. For every additional year of education, your family income is expected to be higher by $6,600. So y hat is the prediction from the line. So we're going to solve this problem of predicting an intercept for people that are impossible right away. We're going to change the scale of x. So think of it this way. Do you guys know where this is an airport map? This is Concourse B. Do you happen to recognize this airport?
Is that up here?
Nope.
That's all I know.
Anyone?
Gates B, Gates.
Oh, that's cute. It's in reference, as if there's something to go to.
I'll give you a hint. It's near your sweatshirt.
Atlanta.
This is Atlanta. Yes, this is Concourse B in Atlanta. It may have changed since I stole this image, but there was a point in time where my now husband and I were commuting back and forth when he was working at the University of Georgia, and I got to know the Atlanta airport very well. But let's say that you're landing in Atlanta. That connects to Cedar Rapids, so that's still a popular connection. And you're starving, and you want to get to the food court, and you grab the map. What's the first thing you need to know to figure out how to get to the food court? The "you are here" sign, right? Yeah, so the star, the "you are here" sign. Once you figure out where you are, then you can figure out if you need to go left, right, and so forth, right? But without that, if you don't know where you are in the map does not help you. Think of the fixed intercept in your data as the "you are here" sign. Like the "you are here" sign should be somewhere in the middle of the map of the data, because then you can talk about what happens as x goes up or x goes down, and the predicted outcome carried by the fixed intercept at the "you are here" sign is someplace where you might actually care where you are. This would be like if you're over in Terminal E trying to figure out how to get to the food court in Terminal B. Like it's so far away, it's just like not relevant. And that's why you get weird, impossible predictions. So the "you are here" sign, the intercept, we always want to make it so that's something meaningful. And the way to do that is to change the scale of x so that 0 means something. So the idea of changing the scale of a predictor so that 0 means something is called centering. You're making a new center point. There are no wrong ways to center, only ways that are more or less weird. So you can think of the previous variable, original education, as being uncentered or centered at 0. I have changed it so that the variable that goes into my model is education minus 12. By subtracting 12 from everybody's education, 0 is the new 12. Now my "you are here" sign, my fixed intercept, is for somebody with a high school degree. Their expected income in thousands is like 27,000. From there, the slope is the same, but what it's in reference to now has meaning in relation to the rest of the data. So it's an interpretation issue to have a reasonable intercept. But everything that we do from now on, and hopefully the rest of your lives, is going to have a predictor that has a meaningful scale where 0 means something. The middle of the data is just fine. I tend to pick points that have absolute reference, like education equals 12 years in this case. The grand mean is a popular centering choice, so it's called mean centering or grand mean centering in that case, if that's what you center around. I chose not to do that here, so like the mean education was like 13.2 years in this data set. But I'm pretty sure no one wrote down 13.2 years as how long they went to school. So I could center around mean education, but then I have to know what the mean is to think about what's high and what's low. If I pick a point where people know what that means, like 12 years, then that has reference even outside of the study. Because mean education in a study could be 17 years, it could be 8 years. It's sample specific. So I'm recasting my education variable so that 0 is now 12. And so this is what it would look like to fit the two models that we've talked about so far.
So when do you do that? Like make education negative 12?
Before you start your modeling in the data set, you would say new education equals education minus 12.
And then how did you find out 12 was going to be like that good? I'm calling it like the tear button, right? How did you find out that 12 was going to be the tear button?
Because I already looked at the descriptive statistics for education and found out what the mean is, the variance, and the min and max, and I picked something I thought would be near the middle. So yeah, it's either something that you get from the sample or you already have in your head sort of as a reference point for a variable. Yeah. So here's what this would look like. Empty model for family income. The empty model, rounding off the numbers just to keep this easy, the mean of family income is roughly $40,000. Okay? That is this line right here. If I know nothing else about you, my best guess for your income is the mean for the sample. That's the one that's most likely. Here it is. So here's the slope across education. So you told me before that what does a slope that's flat mean? No relationship. Why? Because education's not in the model yet. It has to have a flat slope. Doesn't have a chance to have one yet. So across any x variable, any predictor, the slope is flat. Okay? So we can measure then for each of these people how far off their actual education is from the one that's predicted by this flat line. So I'm using this person out here who is very far apart from everyone else. They have education of 20 years. So that gives them, on my new education scale that's centered at 12, 8 years. They are 8 years above the centering point of 12. Their y is 155,000. So all this distance between where they are and the mean, that's E from the empty model for this person. So it works out that E is 115. Their actual income is 115 higher than the mean that is predicted for them and everyone else from the empty model. So if I were to find each person's E and plug that in here, square it, sum it, divide by n minus 1, I get a total variance in education of 1980. So that's my jumping off point. The naive guess. So 1980 is all the reasons why some people make more money than others. Why some people are higher than the mean and some people are lower than the mean. So the square root of that is how far off on average people are from the mean. Once I add in education, the model, the two parameters that are found through the model, beta 0 is the fixed intercept, that's 27. Beta 1 is the slope. So that's this regression line right here. So if I have education of 0, this is my prediction. For every year education, so instead of using the phrase unit, you want to use the actual units if you can. So for every additional year of education, what happens to income in thousands? The slope goes up, right, by 6.6 thousand. So in this case, for this focused person up here, their predicted income is right here on the line. It is the intercept plus filling in their value of education of 8, because they are 8 above the new centering point of 12. That works out to be 80. So their new custom predicted income is 80. Now that's closer, that's better, but it's still not there. So what we
that person's fake, right?
These are all real people, but I'm sure the data have been like bastardized to the point where you couldn't recognize anybody.
So then so this is reactive data, like, so this has already been explained, like
Collected. Yes.
Then why would you predict?
The idea is that we are trying to answer the question, do people with more education have higher incomes?
Okay, so we can't, okay,
That's why.
okay.
In theory, yes, we could take this prediction and transfer it to a new sample, although that's usually less of an interest in the social sciences. So these residuals then, right? The total from where you are to the mean was E before. E now is the difference between where you are and where the regression line says you should be. So this much difference, this much deviation by the blue line, that is still unexplained. That's E. But we're closer than we were. So we need to get credit for the closer. So the difference between the regression line and the flat line, that's explained by the red. The slope explained it. Why is it that this person makes $155,000? Well, they went to college for freaking ever. Now, they still make way more money than they're predicted to, and we don't know why. So even after we condition on the fact that they went to college for 20 years, they're still doing better than they are predicted to, and that's residual variance. That's remaining reasons why they have more income than we think they should. Or like these poor people down here, right? These are like social workers and teachers and stuff, right? That went to school for freaking ever, and they are not raking in the dough.
Yeah, literally.
They're graduate assistants is what they
Yes,
are.
GRAs. Yes, the worst paid master's degrees in the country, right? Yes. So those people down here, so they're making way less. So at this point, we characterize the variance left over. How much is the remaining difference between where the regression line says you should be and where you are for each of these people? And that's 1594. It went down. That's good. So if we enter predictors that are useful, this variance left over, this residual variance of the E's, should keep going down and down and down and down and down until we know all the reasons why some people make the money and some people don't. And learning quant skills will help you make the money. No joke. Okay, questions? All right, so we'll pick this up on Thursday, office hours later today, if anybody wants to come chat. See you then.
So this is, I have a class during office hours. Is there something outside of those that we can maybe schedule?
Yeah. Do you want homework help or do you want to chat about other things?
Homework help,
Okay.
honestly, because I still